Welcome to organic video number 13, which is the equivalent to PowerPoint 20.1c. Our discussion will focus on electrophilic substitution. One ring to rule them all. In terms of accessing your prior knowledge, benzene is the most important idea, although, to be fair and honest, the idea of Lewis acids and bases is helpful here, remembering that a Lewis acid is an electron acceptor. And we learned in a previous video about the word electrophile as an electron deficient species. So let's discuss benzene for a little bit. Some syllabus statements that we've already worked on together in previous work on organic. Benzene is an aromatic unsaturated hydrocarbon. It is the simplest aromatic hydrocarbon compound, or arene, and each carbon-to-carbon bond has a bond order of 1.5. Benzene is susceptible to attack by electrophiles. Discussion of the structure of benzene using physical and chemical evidence. So these are things that we'll talk about a little bit here to review benzene. This is the typical Lewis structure of benzene, alternating double bonds. It can exhibit resonance. It has resonance structures. So I could draw the three double bonds here. If I want to consider the simple structure using, let me erase this arrow. If I want to consider the simple line structure here, that is a typical representation of benzene. C6H6. Benzene has 6 carbons in a ring with 3 alternating double bonds. Each of these carbons happens to be sp2 hybridized. The fact that it's sp2 hybridized means that there is an unhybridized p orbital in every carbon. So what we would normally think of as double bonds here, the pi bond of the double bond, we would normally think of it as 3 pi bonds. The reality is it is a delocalized ring. A couple different structures here. A delocalized ring where these pi electrons are delocalized, and that adds a fair amount of stability to the molecule of benzene. And this means that benzene does not readily undergo addition reactions. And addition reactions are common for alkenes. We have addition polymers, we have addition electrophilic, we have electrophilic addition, which we learned about in video number 12, with the electrophile being attracted to the pi electrons. And in the case of benzene, that addition reaction would disrupt those delocalized pi electrons. And therefore, benzene undergoes electrophilic substitution instead of electrophilic addition. So benzene is not your typical alkene. Different kind of reaction. So here we are talking about electrophilic substitution. We've kind of seen this syllabus statement already, but benzene does not readily undergo addition, but rather it undergoes electrophilic substitution. So the general equation for electrophilic substitution is an electrophile of some sort replaces a hydrogen. And this hydrogen is green just to show you that it got replaced, but the reality is all of these hydrogens are equivalent. So that means any of these hydrogens could be replaced, but it's only going to replace one. Typically this electrophile will replace one. So this is a general reaction equation. No mechanism yet. So in terms of a mechanism, just sort of an overview mechanism. The pi ring is attracted to the electrophile, and so the electrophile actually binds at one of the carbons, and it does temporarily disrupt this pi electron ring structure, but then the hydrogen donates those electrons back to the ring and it reforms the ring, and H plus is replaced, substituted. And so yes, it does disrupt the symmetry of the delocalized pi system, but that delocalized pi system is reformed. If you think about it from an energy perspective, yes, it will have a relatively high activation energy to disrupt that pi system, but it will also release a fair amount of energy in reforming that pi system of delocalized electrons. And so overall, these reactions tend to be exothermic. The first reaction we will learn is adding a nitro group to the benzene using nitric acid, concentrated sulfuric acid as a catalyst, and some heat. So the hydrogen gets replaced by a nitro group, and this mechanism we'll learn in a few slides. Another example of electrophilic substitution is substituting a halogen onto the benzene ring. In this case, we have chlorine, and aluminum chloride in dry ether is the catalyst. Aluminum chloride is the catalyst. This is a scenario where we are given a catalyst and the reaction conditions on some level here, but I do not consider this to be a required mechanism. I don't consider this to be a scenario where you need to remember the reaction conditions. Generally speaking, though, a benzene with a halogen will form the halogenated benzene ring and hydrogen halide, whatever the halogen is. So this could be bromine plus Br2, and it will form a brominated benzene ring plus HBr. So whatever the pattern is, whatever the halogen is, that's the replacement, the substitution. We're not required to learn the mechanism for this, only the nitro group substitution, which is coming up next. So one of our syllabus statements is deduction of the mechanism of the nitration reaction of benzene using a mixture of concentrated nitric acid and sulfuric acid. So concentrated nitric and sulfuric acids are heated at 50 degrees Celsius in order to produce the electrophile, which is a nitronium ion. Sulfuric acid and nitric acid are both strong acids, but sulfuric acid is a stronger strong acid than nitric acid. So the sulfuric acid actually adds a proton, donates a proton to the oxygen here of nitric acid. And that forms this interesting ion, which really, if we put in brackets with a 1+ charge, we have a positively charged nitrogen here in terms of formal charge, a positively charged oxygen in terms of formal charge, which is not common. And we have these two oxygens would share a negative charge because of resonance. So overall, this has a 1+ charge from the addition of the H+. This would be a dative bond. The HSO4-, the conjugate base produced, would be the HSO4- ion. The conjugate acid is this interesting ion, and this ion is unstable. And because it's unstable, this electron pair between the oxygen and the nitrogen leaves that bond and rejoins oxygen to form water. And it leaves behind the nitronium ion. And the nitronium ion is the electrophile. And that makes sense because it has a positive charge, and electrophiles often have a positive charge because they're electron deficient. So now the benzene ring can interact with the electrophile and create this disrupted pi system with the hydrogen and the NO2 bonded here, and this is a positive ion. And then the hydrogen will leave, and what's missing from this picture is this pair of electrons rejoining, and that needs to be included. The book didn't include that in the diagram, but this arrow needs to be included. This pair of electrons is heterolytic fission. It is joining the pi system. So two electrons from the pi system left to form this bond, and so these two electrons rejoin the pi system to remake the 6 pi electrons here that is the stable benzene ring, aromatic benzene ring. We have the nitro group and we have H+. And so this H becomes H+ because it donates both of these electrons to the pi system. And this H+ allows HSO4- to reform as sulfuric acid, which means sulfuric acid is a catalyst. And that is the mechanism for the nitration of benzene. We will absolutely discuss this in class together and review the mechanism, but that is the mechanism that is required from today's video. Overall reaction, benzene plus nitric acid makes the nitrobenzene plus water. The requirement is concentrated sulfuric acid at 50 degrees Celsius. Chemistry in the news. A couple years ago, I saw this in the news. I was encouraged by a former student to add some chemistry in the news to my videos. Carbon nanothreads from compressed benzene. Found that kind of interesting since benzene was a focus here. Connections to other topics, obviously benzene stability and our discussion of Lewis acid and base chemistry and electrophiles. As a summary, benzene does not readily undergo addition reactions like a typical alkene, and the addition reactions require the splitting or opening of a double bond. Maybe not the most scientific terminology, but it is one way to think about that pi bond being split open. Benzene does undergo substitution reactions, replacing hydrogen on the ring with some other constituent. Examples are halogen or the nitro group. A nitro group can be added to a benzene ring by electrophilic substitution with a mechanism required. Thank you for listening. I appreciate your time and attention. There's a Google form if you'd like to submit a question or some feedback. I do not have any checkpoint questions for this because it was really only about that one reaction, and we'll spend some time in class reviewing together. But certainly if you have specific questions that can guide our discussion of the review, feel free to put them in here. Thanks again. Have a good day. I'll see you in class.